Welcome back. All right, so we're talking about vector calculus, div, grad, and curl, divergence, gradient, and rotation of your vector field. Today I'm talking about the gradient, okay? And notice that I have already gotten too lazy to include my little overbars. I'm basically going to drop these, but we know that this operator is a vector of partial derivatives. So the grad operator is partial x, partial y in 2 dimensions. If in 3 dimensions there would be a partial z. I'm going to make my life easy and for now just look at it in 2D. And the gradient of a scalar function f, so if I have some scalar f of x and y, just recall that the gradient of f, sometimes this is also called grad of f, is a vector field. So it takes a scalar and creates a vector field, partial f, partial x, partial f, partial y. So when you hit grad with an f, you literally just put an f here. So if I had grad f, there would be an f here, and you would apply the partial x to f and the partial y to f, and you would have those in the two components of your vector output. Very simple to compute. We could create an example. For example, if f was, I don't know, x squared plus y squared, then the gradient of f is going to be the partial of this with respect to x, which is 2x in the first component, and the partial of this with respect to y in the second component, 2y. And essentially what that's going to do, if I plot that as a vector field in x and y, where maybe this is the origin, what we're going to have is as x and y get bigger, this vector field gets bigger in the x direction. So it starts off small in the x direction and gets bigger and bigger. If I start in the y direction, for larger y, it gets bigger and bigger. And similarly on the diagonals, the farther I go, it gets bigger and bigger in kind of all of the directions. So very, very intuitive, easy to compute for a given scalar function, x squared plus y squared. This kind of makes sense because this function also gets bigger and bigger as I get higher in radius. X squared plus y squared literally is like a big paraboloid if I look down, on this kind of x, y. And if I look down on that in this x, y coordinates, it kind of makes sense that my gradient increases as I go farther away because this gets steeper and steeper. Okay? So that's how you compute the gradient. This is kind of mathematically what it is. A couple of interesting properties here. The gradient is a linear operator. In fact, this nabla operator, this del operator in general is a linear operator. So grad is linear, which specifically means that if I take the gradient of some function f1 plus another function f2, it equals the gradient of f1 plus the gradient of f2. And you can convince yourself that this is true because basically if I had f1 plus f2, I would take the partial of the sum of them in both rows. And the partial derivative is a linear operator. So partial of f1 plus f2 is partial of f1 plus partial of f2. So you can verify that this is true. And also that the gradient of some constant a times f is that constant times the gradient of f. So this is really important. Linearity means that superposition holds. If I write down a differential equation in terms of the gradient operator, it's a linear differential equation, and superposition will hold. If I have 2 solutions and I add those solutions, there's still a solution when you add them together. So linearity is a really important property for differential equations and for operators in general. And I just want to point out that the gradient is in fact a linear operator. Okay, a couple more examples of the gradient. This is one that I've given you a few times, but I really like it. So if I take the gradient of a temperature field, T of x and y, And let's say that that temperature field is going from hotter to colder. Okay, let's say maybe I have a blowtorch and this is a metal plate, and I hit this with a blowtorch for 10 seconds, and then I let it go. So it's hot in the middle, cold on the outside. The gradient of this temperature will be a vector. At every point, I will have a grad t, and that grad t is a vector of partial t partial x and partial t partial y. It will literally have an arrow direction telling me how fast that temperature changes in the x and y directions. And every point, it will point in the direction of the maximum rate of change. So the gradient of temperature tells me what direction is locally the fastest way to climb that temperature gradient. It's kind of why the name stuck. And so I always like to give a homework question or an exam question to my students, and I think they all think I'm crazy, which is, okay, you're an ant flying around in a room and you're cold. Or sorry, ants don't fly. You're a bee flying around in a room and you're cold, and there's a heat source. In what direction do you fly to get there as fast as possible? And if they have the temperature distribution, all they have to do is compute the gradient at that bee's location right now, and they'll go towards that as fast as possible. Again, I mentioned earlier, this is how we optimize functions in lots of optimization problems mathematically, is by gradient descent. I would literally take steps along the gradient direction until I climb this hill, and that's a pretty fast, efficient way of finding the optimum value, the maximum or the minimum of a function. That's how we train machine learning algorithms like deep neural networks with stochastic gradient descent, exact same gradient. Okay? Sometimes it's a bee flying around in a room. Sometimes it's a billy goat trying to climb a mountain as fast as possible. That billy goat still computes the gradient of the altitude to climb as fast as possible. Okay? Good. A few other things I want to point out. You can use this gradient to compute what's called a directional derivative. So I'll just write that out here. So the directional derivative and essentially the directional derivative is literally the derivative of f, my scalar function f, in a direction v. So this is kind of cool. We're used to being able to take the derivative of our function in the x direction, that's just partial x. We're used to being able to take it in the y direction, that's partial y. But what if I say, okay, take it in this v direction? I've got some random vector v. How do I take the derivative of f, the rate of change of f in that direction? Is f getting bigger, smaller? By how much? And mathematically, we say that this is the directional derivative of f in the v direction. This is how we write it. It's the derivative of f in the v direction. And it's super simple. It doesn't get simpler than this. It's just v dotted with the gradient of f. Remember, the gradient of f is a vector, and I can dot it into this direction, v. So I literally just see like where is grad f pointing, and I dot it with v, and that tells me how fast. And if they're perpendicular, then the directional derivative is 0. Actually, I kind of drew it so that the gradient is almost perpendicular to this v, in which case the directional derivative would be 0, which means if I take a small step in that direction, my temperature doesn't change. There are directions like that. And you have to normalize by the length of this v, because someone might give you like a v that's 10 units long or 0.10 units long, and it shouldn't matter what the length of v is. So the directional derivative, also super important. Okay, one more example. I want to really like drive home how much I love the gradient, how useful it is. And I feel like when I'm learning math, I like to see it a lot of different ways because maybe one of them clicks. So the gradient allows me to compute the rate of change of a scalar field in the x and y directions. That's literally the rate of change in the x direction, the rate of change in the y direction. It allows me to compute directions of fastest rate of change. It also allows me to take the derivative in any old direction. And another example of the gradient beyond the temperature distribution is gravitational potentials, okay? So an object, maybe I'll do pink over here. So another application is an object in a gravitational field. Okay, and I want to kind of try to remember how to actually do this. So we have Newton's law of gravity. Okay, and Newton's law is something like the force, and remember force has a direction, it's a vector. The force is equal to, if I have like, I should probably draw a planet here. So if I have planet Earth, let's actually make this kind of fancy, right? So we got some continents. Really bad at drawing Earth. Okay, we got some continents over here. Earth. Earth has a gravitational field, right? And that gravitational field always points towards the center of Earth. We know that that's true. And in fact, the gravitational field is stronger the closer you are. If you go way, way out, I'll only have a little force, a smaller force. Okay, so it's always pointing into the center, and it's bigger when you're closer. And you can write that down, Newton's law, as minus little m times big M times the gravitational constant divided by the radius cubed times some radius vector, where, how do I want to say it? So that's if I have some point out here with mass little m. Of course, Earth has mass big M. And this r vector is always pointing towards the center of the Earth. Okay, this is always the vector pointing towards the center of the Earth. And this has magnitude r, so I need another r down here. We know that the force decreases as r squared, and then I need another r to counteract the magnitude of this. And that's it. The force always points in the radial direction, and it has magnitude given by this expression here. Okay, that's all fine and good. This has nothing to do with the gradient so far, except that this is a potential field. This is equal to minus the gradient of the potential energy of this object. So any object at some radius r is going to have a potential energy, and its potential energy increases the farther out you go in r. And literally, the gradient of that potential is what gives rise to this, this force law here, where the gravitational potential V is equal to minus little m, big G over little r. That's it. Literally, the potential increases as you go farther away. And if you grad this object, you arrive at this force law vector field. So I highly encourage you to actually do this exercise. Write this out in Cartesian xy or xyz coordinates and compute its gradient and convince yourself that it is actually the right gravitational potential. Okay, very kind of useful idea. This is also useful if you have a roller coaster on Earth. I love roller coasters. In fact, I'm filming this at 7 p.m. the day before I'm about to move across the country to California for sabbatical. That's how much I love gradients, and I love teaching you about gradients. And on the way, we're going to go to Santa Cruz, and we're going to ride roller coasters at their fair. Okay? And the exact same potential, if I write the potential energy of a car on a roller coaster, I can create a vector field of the forces at every point on that roller coaster, you know, by creating the gradient. Okay, that's how gravity is acting on the car at all of those locations. Okay, so this is the gradient. We're going to do the same thing for div and curl, and then we're going to start putting these objects together and showing how these kind of partial derivatives and these operators are the building blocks of vector calculus, conservation laws, and partial differential equations. All right, thank you.